Now we look at inequalities. So equations are when we have two mathematical expressions and we combine them using an equality sign. Inequalities is if we join them by or connect them by using an inequality sign. So what inequality signs do we have? Here we have this meaning larger than. So for example, 6 is larger than 3. Or this smaller than. So this on this side is smaller than that side, and here is that on that side is larger than this on that side. This means larger than or equal to. Since it's a combination of larger than sign and equality sign. And this means smaller than or equal to. So for example, 3 is smaller than 6 is true. 3 is larger than and equal to 3. Is that true? Yes, it's true. 3 is not larger than 3, but it's equal to 3. And it says or, and that's a logical or, mean that at least one of these should hold for this to hold. And one of these holds because equality holds. Or for example, minus 2 is smaller than or equal to plus 2. So all these are true. So that just illustrates what these symbols mean. Okay, let's make an inequality. So let's say we have this one, for example. And so this is a mathematical expression, and then we take another mathematical expression. For example, what should we take? We can take 7. Now we want to find out, or we want to find the solutions to this inequality. So we connect these two mathematical expressions with this inequality sign. Then we have made an inequality. An inequality, we are looking for all the solutions to this, meaning we are looking for all the x's that makes this true. Okay, so that's similar to how we try to solve an equation. We try to find all x that make this true. We also try to find all x that make this true, but instead of an equality sign, we have an inequality sign. So we try to find all the x's that make the left-hand side larger than the right-hand side. Also here we can draw a figure with weights to compare with, or analogy. So let's say we have this balancing weight here. On the one side we put the unknown weight, two identical unknown weights, and then a weight with 3 kilograms. Okay, on the other side we put this weight of 7. Now we know that the left hand side is heavier, because you see that this should be heavier than that. So you should have this situation. If we now remove things from this side and at the same time remove things from the other side, then this situation still holds. So if this side is heavier than that, and we remove, for example, 3 from both sides, then this side is still heavier than that side. So let's remove 3 from both sides. Then we have 4 left here. So if you have an x that makes this true, that is makes this inequality true, then it must also make this true, since we have removed the same amount on both sides. Meaning that this inequality must be true if this is true, and vice versa. So these have the same solutions. these are equivalent. These are two equivalent situations. So also here we are trying to transform an inequality by exchanging it with equivalent inequalities, meaning that inequalities have the same solutions. How could we continue now? Yeah, we could have two x's on the left hand side. So we could remove one of them. So we half the weight on the one side, and we need to half the weight on the other side. So you have two here. So if you have an x satisfying this, making this heavier, then it's still heavier if we remove half from both sides. And this last situation corresponds to this inequality. So the two last inequalities are equivalent. So we see that these three are all inequalities are equivalent, meaning they have the same solutions. But now we have arrived at one that is very easy to solve. The last one is easy to find the solutions to because it's almost written explicitly. So which x's make this true? That is of course all x's that are larger than 2 that makes this true. So all solutions to the first one is all x's that are larger than 2. So we have arrived at that this inequality have the solutions x larger than 2. All x larger than 2 are solutions here. And for all x less than or equal to 2, this does not hold. So that's how you solve an inequality. You solve it very similar to how you solve an equation. However, there are some differences here that we need to be careful of. So also for inequalities, we can add and subtract any number on both sides. So if you add or subtract any number on both sides, then we make equivalent inequality. We can also multiply and divide any number on both sides. But not 0. So we can't multiply or divide both sides by 0 and expect to have equivalent inequalities. Nor can we, or we also have to keep in mind that if we multiply or divide by negative, so if you multiply or divide by negative on both sides, then we have to switch inequality sign. Switch or flip maybe. Okay, so we need to see some examples to see what we mean by that. So for example, if we have so let's say we have this inequality. Okay, then we want to transform this to equivalent inequalities stepwise. We could, for example, now subtract on both sides any number or add any number. Let us, for example, subtract 3 on both sides. Then we will get this. So if we subtract 3 on both sides, then we have 4 minus 3, 1 here. Okay. Now we can move over, of course, 2x to that side, but just for argument's sake, move over 3x to that side, or we subtract 3x on both sides. That will give us minus 5x on that side and 1 on that side. Okay, so we have subtracted 3x on both sides. That is allowed to give us equivalent inequalities. So what should we do next? Yeah, it's very tempting now to just to divide by -5. So let's do that. But then we have to keep in mind that if we divide or multiply with a negative number, then this should be switched or flipped. Then we need to change it to the other direction. So maybe instead of switch or flip, we can say change the direction of it. Okay, so on this side now we have x is -5 and -5 cancel. And this becomes -1/5. So we see that we have that. Why did we need to flip or switch direction on this one? Change direction on that one? It's for the simple reason that it turns out to be correct and incorrect if you don't. But let's motivate a little bit further than that. Let's first of all just see if we didn't go about doing it this way. Let's say we did an alternative way. So instead of, let's say we want to avoid the problem of having a negative on this side. So instead we move over 4 to the other side here. Then we get -1 there. 3x here. And now we add 2x to both sides. So we get the 5x on that side. But now it has a plus sign. So now let us divide both sides by 5. And here we divide by positive numbers, so here we don't switch directions. This is -1/5. Here's x. But now we see that these two solutions are identical. Here says that all x's less than -1/5. Here also says all x's less than -1/5. So this is just written in the opposite direction. Of course, we can just move it to the other side. Instead of writing like that, if we want the x on the other side, we just can rewrite it like this. So this means the same thing. So we see that we have the same solution here. So we say if we didn't switch side on this one, then these two solutions wouldn't be the same. So we need to switch direction on this when we have divided or multiplied by a negative number. And for example, if we would have this sign instead, and if we multiply or divide by a negative, then we need to switch to that. Let's see if we can motivate that also in another way. Okay, we have that 2 is less than 3, obviously. But we also have that -2 is larger than -3. Why is that? Yeah, we can just put them on a number line if you don't see that directly. Here we have 0. Here we have 2, 3, -2, -3. We see that 2 is less than 3, this one. And -2 is larger than -3 because -2 is to the right of -3. So -2 is larger than -3. So these two are true. Okay, so let's say we will start with this one. 2 less than 3. Let's say we multiply both sides by -1. Okay, if we didn't switch here now, what would we get then? We got -2 less than -3. So if we didn't switch this, we say that we got a contradiction to this one. Because this one and this one doesn't say the same thing. Here are a different direction on this one. So we see that when we multiply both sides on inequality, to get the correct result, we need to flip direction here. So we see that this is the same as this. So if we didn't flip, it wouldn't turn out correctly. We can also see it like this. Here we can subtract on both sides with 2. That will give us 3 minus 2. And then we could subtract both sides by -3. Then will give us like this. Okay, so we see here we have this. Here we can just change sides on these two, right? -2 on that side, -3 on that side. Then of course you have to change direction. These two are exactly the same, just reading them differently. So you see, if we start from this is same as that. And this we can write as -1 times 2 larger than -1 times 3. So you see that we have this one, and then of course identical to that is this one. So you see the effect of multiplying on both sides by -1 switches this here. So that's some ways of motivating y. So why do one want to bother about inequalities? Are there real world situations where you can come across it? Yes, of course, very many situations you can come across. Let's take just one example. So let's say we have 2 taxi cabs, different companies. The price for one company 1, they have a fixed price of $5 and a kilometer price of 2. And another taxi cab, they have a fixed price of only, let's say, 2. But they have a kilometer price of $3. Then of course, if we don't travel that far, it's cheaper to go with this with the lower fixed price. But how far should we go so that it becomes more inexpensive to go with the first one? So how far should we travel so that we have that the price for the first one is larger, not larger, but smaller than the second one? Yeah, then we can solve this inequality. The left hand side is 5 plus 2x. The right hand side is 2 plus 3x. Okay, solving this now, getting x's on the same side, we get x here. 2 over to that side, we get 3. And here we can just change sides, it looks more nice. So we see we got this one. So we see that if we go more than 3 kilometers, it will be cheaper to go with the first company, even though their fixed price is larger. So that's just a very simple example in real world, but of course there can a lot of other examples. So far we have seen only linear equations, as no powers 2 or higher. But we don't have to limit ourselves to linear. Let's say we want to solve this inequality. So this is a quadratic inequality. So what solutions does this have? We can note the following. We see that for which x are x squared equal to 1. Yeah, that is, of course, that's an quadratic equation that happens when x is equal to plus or minus 1. Okay. And then, what can we say then? We see that when x is smaller than 1, so this happens when it's 1, but greater than minus 1. So let's draw a number line to more easily see what we are doing. So here we have 0, x. Here we have 1, minus 1. So when we are here and here, x squared is equal to 1. When we are in between minus 1 and 1 here, then the x squared is smaller than 1. So in this area, x squared is smaller than 1. And when we are to the right of 1 and to the left of 1, of course, if we square a number larger than 1 here, or more negative than minus 1. So it will become larger than 1. And also here, because the signs cancel. So we have like this, and here in the limit we have x squared equal to 1. So the solutions are, where are x squared larger than 1. Therefore, all x larger than 1 and all x less than minus 1. So the solutions to this inequality in this case is given by that. So here we have to reason really. You can reason in this way. You have to divide up in cases. You see the limiting cases. Where are they equal? Where are they larger? Where are they smaller? So in this case we can solve it like that. So this is solving it algebraically. We could also solve it graphically. That we'll see now. Okay, so we want to find out x squared. So x squared we have here. Let's change the color. And then we have f of x equal to 1. But that was not what I wanted. Y equal to 1. Okay, so this line here, let's make it blue. So now we see here is our curve x squared. And here is the line y equals to 1. So our question now is, where is x squared larger than 1? That basically means, where is this curve above the blue line? That's the same thing interpreted graphically. So x squared larger than 1 means that this curve should lie above 1, this blue line. So you see it happens here and it happens here. So you see it happens when x larger than 1 or smaller than minus 1. And we see that x squared is less than 1 here, between minus 1 and 1. So you see here we can read off the same result as we did algebraically. But again, we have the same disadvantage when solving graphically. It's easier perhaps sometimes to see, but sometimes hard to read off exact values. Here we can guess that the exact value is 1, but no matter how careful we draw it, we can't be 100% sure that it's equal to 1 here. We have to do it algebraically. So we only get approximate solutions. As a final example, let us look at this. So we have this inequality. So what are the solutions to this inequality? That is, for which x is x squared larger than x. So let's first solve it algebraically. Here it's tempting perhaps to divide both sides by x. Let us see what happens if we do that, because that is not really allowed. If you divide both sides by x, then this becomes x and it becomes this. So let's put this in parentheses for the moment. We see that if we did it in this way, we get this solution. But what is the problem with doing this way? The problem is that we don't know what x is. So if x is negative, then we need to switch here. And if x is 0, we're not allowed to do this at all. So since we don't know what x is, it's dangerous to do it in this way. So it's better to avoid dividing by something that could be negative or 0, because we don't know when it is. So let's, instead of dividing, let's do it in this way, more carefully and cautiously. Let's instead subtract both sides by x, because that is safe. It doesn't matter what x is, we can subtract it on both sides. Then we can now factorize. And that is also safe, because it's just rewriting the expression on the left-hand side. Now we want to find out here, when is the product of these two numbers larger than 0? Okay, so how can we find out that? Yeah, it's larger than 0 when these have the same sign, because plus times plus is plus, and minus times minus is plus. So when they have different signs, this is not true, and when they have the same sign, this is true. Okay, and a technique for doing in this case can be to draw or solve it in the following way. We draw for each of these numbers, two numbers, we draw a line. And also we draw one line for the product. Okay, so here is one line for x. Here is a line for x minus 1. And here's a line for the product. So this is the technique we're going to use. Let us put 0 here. So here we have 0. So these are number lines really. Okay, for what values of x is x positive? Yeah, seems like a silly question. It's of course here. Here x is positive, and here x is negative, and in between here it's 0. Okay, where is this positive and negative? Yeah, it's positive, or it's 0 at 1. So if x is equal to 1, it's 0. It's positive if x is larger than 1. And it's negative if x is smaller than 1. That was the wrong color. So here we have blue for negative and red for positive. So let's just make that clear. So this means plus. This means minus. Okay, so to the right of 1 we have plus, and to the left minus. Okay, so when is this plus or minus? That's what we are really trying to figure out, because this inequality. Where is it positive? Where is it larger than 0? Then we see that here the first one is plus, here the second one is plus. The two numbers are both plus. So that means that the product is plus, larger than 0. At 1 of them is 0. That means its product is 0 there. Between 0 and 1, one of them is plus and another minus. Then we have minus times plus, then it's minus. Here one of them is 0, this one. So here it's 0. And to the left of 0, both of them are negative, so their product is positive. So doing this way, we can now read off the solution. When is this larger than 0? That's what we're trying to find out. It happens here and here, that we can see. So we see that for now, when x is smaller than 0, not equal to 0, because then it's 0. So when x is smaller than 0 and x is larger than 1 here. So the solutions to this inequality, we started with this one, is this. So if we now go back to this case here, what happened here? We said we did this a sloppy way. We actually got right on one part, but we lost this part. So you can't do it in this way if you want to be on the safe side. Okay, so this is doing algebraically. Algebraically, this inequality has these solutions. You can also do it graphically. So let's now find out where is x squared larger than x. So let us draw these two curves, or these functions, x squared and x. So we see we have this situation. So the red one is x squared, and the green is x. Then we ask the question, where is x squared larger than x? We see that happens when the red curve is above the green curve. So we see here it happens that the red curve is above the green. So when x is larger than 1, it's bigger. And it also happens here when x is smaller than 0. So here we can see graphically that x squared is larger than x when we are here and when we are here. And in between it's smaller, and here they are equal. So in this way you can also read it off graphically. But again, we need to keep in mind that graphically only gives us estimates, not exact solutions in general. So if we want to have exact solutions, we should do it algebraically. But it's important to be able to handle both situations, both graphic and algebraic.